What's up, scholars? We're going to go through questions from your practice quiz. And the goal of this is I want to sort of do this problem as if I was solving it myself on a test. I'm going to try to think out loud and write down and annotate this problem number one and possibly a few others here in a moment. Now, I'm going to solve this much slower than you would solve this on an actual exam, but the goal here is to show you all the different bits of physics that we've learned in this unit and in previous units that I'm going to use to help me here. I'm also going to try to pay as much attention to detail as possible so that you can realize that you need to grasp these details when they're available to you. This is a skill that's very difficult, and frankly, this is my second year teaching AP Physics when I'm recording this video. I'm also learning the best ways to talk to students about solving these. So let's jump right into this first question. So I crack open my new test. Question number one, I see it's a graph. Before I read it, I'm going to make sure I look and notice that I've got velocity and time. I'm also going to notice that one of my objects starts with a negative velocity and one starts with a positive velocity. And then they look like they have roughly the same velocity at the end. Okay, so I've inspected this a little bit. Let's go ahead and read the question now. It says, object X travels across a horizontal surface and collides with object Y. Ooh, that sounds like the thing we just did in class. I'm going to pause the video and quickly sketch a graph or a picture of that. Now you can see I've got a beautiful drawing here of the before the collision. I need to, I haven't even read the whole problem, I need to wrap my head around what they're doing before the collision, and then maybe we can sketch what they're going to do after. So one of the objects, I'm going to call this one M1, the first mass. It looks like it's got a positive velocity and it's a bigger velocity. So I'm going to draw an arrow like that. We'll call that V1 initial. And the other object is actually going in the opposite direction. It's a negative initial velocity. I'm going to draw the arrow just a little bit smaller. We'll call that V2 naught initial. Now, let's continue reading the question. I got excited because this sounds like the experiment that we did. Oh, wait, no. Let's not do that. Let's notice that after the collision, they both have a mutual velocity. They're stuck together. I'm going to write that here. They're stuck. And they're going to move off together. So I'm going to draw this again very sloppily. Oops, whatever. They're stuck together with some v final. So they're going to have a mutual velocity that looks like it's right around 1 meter per second. 1 meter per second. This one was, v1 was 4 meters a second, and this one was negative 2 meters a second, going the opposite direction. So this one overtakes the other one. Ooh, I also know these both have the same mass. So mass for both is is 2 kilograms. All right, let's get back in and actually read the question. So the next situation says, velocity is a function of time for object X and Y before, during, and after the collision shown in the graph. Okay, let's see if we can make sure we're clear on that. So this looks like it's before. This curvy bit looks like it's during the collision. So the collision lasted from about 0.3 of a second to about 0.6 of a second. That's interesting. We don't need to know that here, but it's good to note. And then this part where they're stuck, that's the after bit. All right, let's keep going. Both objects have a mass of 2 kilograms already. So that, which of the following correctly describes the momentum P of the system and the kinetic energy K of the system? So I know we've spoken quite a bit about the difference between like vector and non-vector quantities. Here they're very careful to put the vector hat, which they aren't always, and I will be honest and say I'm not always careful to put that in there. But what that's reminding us is that the momentum in the beginning is a combination of these two objects, the total momentum, and that it's a vector. So I don't think we're going to need to calculate, but it's just a good reminder. This one, because it's the same mass and a bigger magnitude, a bigger speed, 4 meters compared to 2, this is going to have a bigger momentum. So the overall momentum is going to be to the right. It's going to be overall positive because mass 1 is the same mass but moving faster than the other one. That makes sense too, that it would overtake it. All right, let's keep going. Which of the following correctly describes the momentum of the system and the kinetic energy of the system? So this is one where we want to make some eliminations. And when you do this yourself, I'm going to ask you to make at least 2 eliminations to the best of your ability. We know that momentum is always conserved in a closed system like this one. There's only 2 objects. We're not told that there's friction or anything, so we're going to ignore that. So anyone that says that momentum is not conserved, we can just right away nix those. And then our job is to do the hard work to see, is the kinetic energy conserved. Now, if I'm doing this on an AP test, and I know that they hit and stick together, I'm pretty clear that that's a very classic inelastic collision. So I'm going to jot that here as a note. Hit and stick is pretty much always going to be inelastic. That means we're going to lose some kinetic energy. So if I was doing this on a test, I would probably jump straight to B, which I'm pretty sure is going to be the right answer, but we can quickly check. If we're kind of going to the trouble of doing all this work, let's quickly check without doing any actual calculations. So if I'm going to do this kinetic energy before, it's 1/2 times 2 kilograms times 4 squared. Those cancel, so I'm going to get, wow, 16 joules. This one is going to be 1/2 times 2 kilograms, that should be meters per second, times negative, we're squaring that, meters per second. So those cancel and I get 4. So I have 20 joules to start with. Here I've got 1/2 times 2, which cancels, times 1 squared, so 1 at the end. So I have 20 joules before and just 2 joules after, which is not surprising because they hit and stuck together. They're moving incredibly slowly after the fact. So the correct answer is indeed B. Now, if we look at the clock, I think I started talking about a minute in. That took me 5.5 minutes to solve, talking out loud and thinking through everything. Remember, we probably only have about 2 minutes to solve a problem like this. So what would I cut out if I was doing it? Well, I already mentioned one. We didn't really need to calculate. We know this kind of collision is going to be inelastic. I didn't have to draw a picture, for sure. I didn't have to do all of these labels. But what I do need to do is think of the entire problem, use what I know from our experiments, namely the hit and stick is almost always going to be an inelastic collision, and the basic fact, this is like a base level fact, that momentum is always conserved. So I can eliminate these. These are easy to get rid of. Easy. So when you do this, I want you to do just about the same level of detail. It's going to dramatically increase your chance of getting the problem right. Let's do one more. Look at number 4. Very simple, no pictures. It says, how does an air mattress protect a stunt person landing on the ground after a stunt? Now, this one has 5 answer choices, so our strategy to do some eliminations, I think, is really helpful here. It's likely you'll be able to, if you're on your, on top of your stuff, be able to quickly get rid of 2 choices, then make a call to get rid of a third, and then we'll have to do like a 50-50 guess. So let's take a look. This says we're trying to have a person protected. So I'm going to draw them falling. They're going to fall and hit an air mattress. They're going to have some initial velocity as they're falling, and then this mat is going to apply a force up on them so that their final velocity is going to be 0. Now, it sounds like, we kind of don't have any choice. They're being dropped from a particular height. So the change in momentum of this person is going to just be the, delta mv. We know the final velocity is going to be 0. We know their initial velocity is going to be the same. Using kinematics, they're always going to hit the mat with the same speed. So we don't really have any control over their change in momentum. What we can do, and we talked about this is in some of our other work with collisions, is think about inelastic collisions, or how we can distribute that energy over the longest possible period of time. When it says protect a stunt person, what they mean is we want to keep the maximum force low. So just like I said, we don't really have any control over the momentum. This is a fixed number. Fixed. That is the equation for impulse. The change in momentum is the force times the time. So some options we can do are to decrease the maximum force. We have to increase the time. So let's see what we have as answer choices. We haven't even started to read them yet. We'll try to make some quick eliminations, and if we're not sure if we can eliminate it, we'll hang on to it for a second. So this says it reduces the kinetic energy loss of the stunt person. Now, that's not a good idea. If you still had kinetic energy left over at the beginning, left over after you crashed into the air mattress, you'd still be moving, which means that your final velocity isn't 0. That would be even more change momentum. That's really bad. You really don't want to keep moving after the collision with the mat. B says it reduces the momentum change of the stunned person. Now, that one I think I kind of already addressed. We'll put a star by that. I think we can eliminate it. But we can't really do anything about the momentum change. Again, we can't change their mass. We can't change their initial and final velocities. So their momentum change is going to be what it is. We have no choices there. So probably going to get rid of B, but let's keep going. C says it increases the momentum change of the stunned person. So that would be even also really bad. That's like A. We don't want the momentum change to be smaller, or to be different. I guess if you could make it smaller, that would be ideal. But we have to take them from whatever speed they are at the moment before they hit the ground. So this V0, by the way, is like the moment before they hit the ground. And we have to take them to a stop. So we can't change anything about their mass unless they like lose a limb or something during it, which we're not going to do. So far 2 good eliminations and 1 possible one. Let's look at the other ones. D says it shortens the stopping time of the stunned person and increases the force applied during the landing. Now, increasing the force sounds really bad. Shortens the stopping time is sort of the opposite of what we want. We spoke about this in class. When you see people do parkour, or even I know some of you have been rock climbing or bouldering, when you hit the ground, you want to roll or lengthen the amount of time. This was why the underdog was such a powerful thing. So we don't want to increase the force. That's another good elimination. So we've got 2 left. We haven't even read the last one. We think B might be out. Let's check E really fast. It lengthens the stopping time, which is what we said we want. That's good. Remember, delta P, that's a fixed number. F times delta T. These 2 numbers multiplied together have to equal some number. Let's just say it's 100. So if we make delta T bigger, then the force has to get smaller, which is safer for the person. So the answer here is definitely E.